Thing is slow today. Okay, all right, so let me go back to here. But before I begin, let me ask you guys about the test. Have any of you done the test yet? Test number 1. I guess not. Okay, well, let me see. Somebody just responded. No, there are no multiple choice questions. And this is an answer to Rosiana. Didn't get your last name. But no, there are no multiple choice questions. Pretty much the questions are similar to the questions that were in the assignments that we did or that you did. All right, so, oh, Bizra, that's her name, Rosiana Bizra. So that's the answer to your question concerning that. So let me just say that the test is now available. I submitted the test last week, Thursday. There's some confusion because there are some new rules or new procedures for submission of tests and so on. Because some of you were trying to sign up for doing the test and you were told that my name is supposed to be on some list. And when I called over there this morning, the lady I spoke to said something to the effect that, that particular issue is not finalized yet. So I don't know exactly what's going on over there. All I know is that the test has been submitted, as well as the tables that you're going to need. And each of you will also get a sheet of scratch paper to work with. And all you need to do is call over there and make your appointments and do the test over there. So that's pretty much all I can say as far as that is concerned. All right. Okay, let me see here. Oh, right. Okay, so Miss Stepinski, and I hope I'm saying right, I'm doing right by you to say Miss. Yes, all you need to bring is a pen, preferably a blue or black ink pen, and your calculator, right? You don't need to bring anything else, or everything else will be provided for you. And somebody here is asking, where do we find the number to call? All I can say is, if you go to the college's website, let me see if I can find it here. Let me minimize this here. And if I scroll down, you see where it says, I'm sorry, not scroll up. Where am I going? You go to academics, and then you see where it says testing and assessment, and the number should be provided there for the testing center at the different, that's the number right there. And you can click on these to schedule the test. I think everything is done electronically now, all right? So somebody was saying you can only schedule online now. Okay, so I guess that's the case. I thought you can call like what used to happen previously. So basically this is where you go to schedule your test, and somebody's placing or posting another number. So I guess you can reach them by that number as well. I guess it depends on which campus. I don't know. But just try it and see if you can schedule your test and be able to do it next week. And I think somebody asked when is the last day for doing the test, and that last day will be Friday. All right. So basically, you're from today to Friday to do that test. And I see one new message. Let me see here. Oh, somebody's just saying thank you. Okay. So with that out of the way, we're going to continue with today's lecture. Now, last time we were here, we did energy, chapter 10. Now, you might be wondering, why have I skipped to chapter 13 to begin today's class? And the reason why is because chapter 13, as far as I am concerned, is a natural follow-up topic to chapter 10. In particular, because in chapter 10, we were introduced to the concept of temperature and what it means. And what you're going to find is that temperature will also become important when it comes to gas laws. Let me see, somebody just posted a message. Oh, somebody says, so there's no multiple choice. Yes, I answered that question already. There's no multiple choice questions in this test, this upcoming test, test number 1. Okay, so as I was saying, temperature will become very important when it comes to examining and understanding the behavior of gases. So that's the reason why I've jumped from chapter 10 to chapter 13. And then after I've completed chapter 13, then I'm going to go up back to chapter 11 and then 12. All right. So this chapter deals with gases. Let me go to full screen. Okay. So in order for us to understand the behavior of gases and all that we have observed about the behavior of gases, we have to be introduced to what is known as the kinetic molecular theory. And this is basically the model that is used to understand how gases behave. So the kinetic molecular theory is based on the motions of gas particles. All right, as we're going to see later on, what the kinetic molecular theory says is that the gas particles moves around with high energy and it moves in a straight line. All right. Okay, somebody's asking another question. Let's see here. Oh, okay. Thank you. Who is this? Ardente. She's provided the information, the contact information for all the campuses with respect to the respective testing centers. So you may want to make a note of those numbers. All right. Thank you very much, Miss, I think it's Miss Corina Ardente. All right. Okay, so as I was saying, the kinetic molecular theory is based on the motions of gas particles. And any gas that behaves as outlined by the kinetic molecular theory, we call that gas an ideal gas, right? So what we're going to get into is how an ideal gas behaves at the microscopic level, and then we can understand based on the microscopic level, how things extend to the macroscopic level, how things like pressure and volume and all of that can be explained based on the behavior of the gas particles themselves. Now, key thing you need to recognize is that there's no such thing as an ideal gas that you can find in nature. However, there are many situations where real gases can approximate in behavior to ideal gases under certain conditions of temperature and pressure. And we're going to talk about that later on. So pretty much for the most part in this chapter, we'll be discussing gases as if they're ideal. But it's important that you recognize that ideal gases do not exist in nature, but we can alter the conditions of pressure and temperature so that the behavior of real gases will be approximated to the behavior of ideal gases. Okay, so let's get into the principal assumptions of the kinetic molecular theory. So the first one is that gases consist of very tiny particles, and these particles can be in the form of either atoms or molecules, all right? Then we have the second assumption, which says that on average, the distance between the particles is large compared to the size of the particles themselves. So what that basically means is that if you have a gas in a container, most of the gas in that container will be empty space because of the sheer distance between the particles on average. Another important, and I would probably say this is the most important assumption of the kinetic molecular theory, and that is that the gas particles have absolutely no attractive forces between each other, all right? So basically what we're saying is that there are no intermolecular forces that exist between the gas particles for an ideal gas. The fourth assumption is that in terms of their motion, these particles tend to move in straight lines and they will collide frequently with one another. And also, just as important, they will collide with the walls of the container. And later on, we're going to see the relationship between the collision of the gas particles with the walls of the container and the pressure that is exerted by the gas itself. The fifth assumption is that upon collision of gas particles, there's no energy that is lost when you have these collisions taking place. Basically, what this means is that if you have two particles of a gas colliding with each other, whatever the total amount of energy before the contact or before the collision, the amount of energy after the collision will be the same. So therefore, you're going to have direct transfer of energy from one particle to the other, but no energy will be lost to the environment or anything like that, right? So the term that is used in physics to describe these types of collisions, we say that these collisions are perfectly elastic, all right? Okay, so let's talk about the sixth assumption of the sixth principal assumption of the kinetic molecular theory, and that is that the average kinetic energy for the particles are the same for all gases at the same temperature, and its value is directly proportional to the Kelvin temperature. And we're going to talk about the Kelvin temperature or the Kelvin scale later on. We were introduced to it earlier when we were discussing heat in chapter or energy in chapter 10, but we're going to talk about later on in this chapter how the Kelvin scale was determined. Okay, so for any of you who have done physics, this should be an equation that you should be familiar with. This is the equation for determining the kinetic energy of a moving object, right? We learned in chapter 10 that generally speaking, there are two forms of energy. You have potential energy and kinetic energy. Potential energy is the energy an object has by virtue of its position, and the kinetic energy is the energy an object has by virtue of its motion. And we can calculate the kinetic energy using this formula, which is half mv squared, where m would be expressed, let me write this down here, m would be expressed in kilograms, and v would be expressed in meters per second, which means that the units of kinetic energy under those circumstances will be kilograms meter squared over second squared. And there's a name given to this unit, which we were introduced to before, and that unit is called the joule unit, right? So the joule unit is the same thing as this combination of units, kilogram meter squared over second squared, all right? So that's a formula for calculating the kinetic energy of any moving object, and this is also true for a moving particle like an atom or a molecule. Now, as we said before, all gases have the same average kinetic energy at the same temperature. So if you have two gases at the same temperature, let's say hydrogen and oxygen. In fact, I think those are the two gases I have. Yes, okay, so let's say we have these two gases, hydrogen and oxygen, right? If they are at the same temperature, what that means is that they have also the same average kinetic energy, right? So as you can see here, the molar mass or the, the molecular mass, let me get back out of this pointer. Okay, so the molecular mass of hydrogen is approximately 2, and the molecular mass of oxygen is approximately 32, right? So basically, if we were to write down, let's see if I have the space to do that here. Okay, so let me do this here. Go back to my pen function. So if I were to consider the fact that both the hydrogen and oxygen are at the same temperature, that means that the kinetic energy, the kinetic energy of hydrogen would be equal to the kinetic energy of oxygen. So if I were to write down the equations for the kinetic energy of hydrogen, it would be half the mass of hydrogen times the velocity of hydrogen squared, and then on the other side, the kinetic energy of oxygen will be half the mass of oxygen times the velocity of oxygen squared, all right? So basically, these halves will cancel out, all right? And therefore, we can end up with this expression where the velocity, let me do this up here, the velocity of oxygen squared divided by the velocity of hydrogen squared is going to be equal to the mass of hydrogen make sure I'm doing this right. The mass of hydrogen divided by the mass of oxygen, all right? So as we said before, the mass of hydrogen is about 2, the mass of oxygen is about 32, right? Which means that this works out to be 1/16. So therefore, we can conclude that the velocity of O2 divided by the velocity of H2 is going to be equal to the square root of 1/16, which is equal to 1/4, right? So therefore, what we're saying is that the velocity of oxygen divided by the velocity of hydrogen is equal to 1/4, or we can write it this way. Basically, we're flipping the two terms. the velocity of hydrogen divided by the velocity of oxygen is equal to 4/1. So what this is telling you is that the velocity of hydrogen is 4 times that of the velocity of oxygen. And that is because the oxygen is a heavier molecule and therefore will move at a slower speed compared to the hydrogen. So that's why this statement here is true. As a result, lighter molecules move faster compared to, heavier molecules at the same temperature, right? And that is true pretty much right across the board. And that is based on what we just did right here, all right? Okay, so with that out of the way, let's talk about pressure, all right? And how we measure the pressure of a gas. Now, the definition of pressure here is pressure is equal to force per unit area. So it's very important that you understand that that's the definition, because in everyday language, people tend to use the terms force and pressure as if they mean the same thing. What you need to remember is that by definition, a force is basically a push or a pull, right? So if I'm pushing on an object or if I'm pulling an object, I'm exerting some force on the object. The pressure, on the other hand, is basically the force that is transmitted over a certain area. And therefore, as a result, that's the equation for calculating the pressure based on the definition, right? Pressure is equal to the force divided by the area. Now, the SI unit of force is newtons, and the SI unit of area is meters, meters squared. So therefore, that means that the SI unit of pressure can be expressed as newtons per meters. But there's another name given to this collection of units, and that is called the Pascal unit. PA is the abbreviation, right? So whenever you see the term Pascal, you should understand it's the same thing as newtons per meters squared, all right? So that's basically what the SI unit of pressure is. But there are other units of pressure that we're going to be introduced to. Let me go back to my pointer here. So, but before we get to that, let's talk about the understanding what pressure is in light of the kinetic molecular theory. So if you remember, we said, according to the theory, the particles of a gas are moving at high speeds and occasionally colliding with each other, but most importantly, colliding with the walls of the container. So as you can see in this diagram here, you have a balloon filled with a gas, and the gas particles are moving around and they're hitting the walls of the container continuously. So you literally have billions upon billions of molecules, high energy molecules, moving around, traveling in straight lines, and hitting the walls of the container continuously. And therefore, as a result, they exert a force over the entire area of the inner walls of the balloon. And therefore, as a result, collectively, the gas particles are exerting pressure on the inner walls of the balloon, right? So that's how we understand how gas particles or how a gas exerts pressure. It's as a result of the continuous bombardment of the gas particles on the inner walls of the container. In this case, the container is a balloon, and as a result of the pressure exerted, it keeps the balloon inflated, all right? So that's basically how we use the kinetic molecular theory to explain the phenomenon of pressure exerted by a gas. So as stated here, there are several factors that affect the pressure exerted by a gas. One is the number of molecules present. In other words, the greater the number of molecules, the greater the pressure that a gas will exert, which makes sense, all right? Because the more molecules you have, the greater number of collisions that the molecules will have with the walls of the container, and therefore the pressure exerted by the gas would be increased. Another factor that affects the pressure of a gas is the temperature of the gas. And again, this makes sense because when you increase the temperature of the gas, you're imparting more energy to the gas particles. The gas particles will move faster at faster speeds, and therefore they will collide with the inner walls of the container much harder, right, with greater force and more frequency. And therefore, as a result, the pressure would increase with increasing temperature. Another factor which affects the pressure of a gas is the volume in which a gas is confined. And again, if you think about this in light of the kinetic molecular theory, that makes sense because if you were to, for example, suddenly reduce the volume of the container, then that means that the distance traveled by the gas particles on average as they collide with the walls of the container will decrease, and therefore, as a result, they will collide with the walls of the container more frequently, and therefore will exert a greater pressure on the walls of the container. All right. So those are basically some factors which affect the pressure exerted by the gas. And later on, we're going to actually look at the quantitative relationship between the pressure of a gas and these different functions: the number of gas molecules, the temperature of the gas, and the volume within which the gas is confined. Now, how do we measure the pressure of a gas? Well, if you want to measure the atmospheric pressure, and by the way, the atmosphere is a mixture of gases, as you all know. About 80% of it is nitrogen, and then about 20% is oxygen, and then you have some other gases that exist in smaller amounts. So what you're looking at here is what we call a mercury barometer. This is an instrument that is used to measure the pressure of a gas. And in explaining this, I'm going to introduce another unit of pressure that is oftentimes used in chemistry. So how do we make this barometer? Well, we firstly have a trough, which is filled with mercury, which is a liquid metal, the only metal that exists as a liquid under normal room temperature conditions. And we fill a tube filled with mercury, right? And then we invert this tube into the mercury trough here, and then we wait a while. And if the tube is long enough, then what's going to happen is that the mercury level will fall to about 760 millimeters of mercury. Now, what you should recognize is that this column of mercury is actually supported by the atmospheric pressure that is exerted on the surface of the mercury inside the trough, all right? So basically, we can use the length of the mercury column here as a way of expressing the magnitude of the atmospheric pressure, because if the atmospheric pressure changes, let's say it increases, then it pushes the mercury column up further, and therefore that height would be proportional to the atmospheric pressure that is exerted on the surface of the mercury outside of the tube here in the trough, all right? So this brings us to a new or different unit of measuring the pressure, and that unit is based on the height of the mercury column right here, right? And this, well, actually 2 units of pressure would be introduced here. One is what is known as the atmosphere, and the other one is what we call the millimeter of mercury unit. And I think in the next slide, let me see here, yes. So in the next slide, we have the relationship between the atmosphere unit, and here we have the millimeter mercury unit, all right? So by definition, 1 atmosphere is equal to 760 millimeters mercury. And you'll notice just above this here, we have what is known as a torr unit, right? And it turns out that the torr unit, by definition, is the same thing as a millimeter mercury unit, right? So basically 1 millimeter mercury is equal to 1 torr. Now this here is expressing the pressure in terms of centimeters of mercury. So it's a simple conversion from millimeters of mercury to centimeters mercury. You should be able to do that because by now you should be familiar with the metric system with respect to length. There are some other units as well. We have the kilopascal units, which is related to the Pascal unit that we talked about earlier. So basically, according to the SI system or the metric system, 1 kilopascal is equal to 1,000 pascals. So therefore, we have 101.325 kilopascals. So to convert that to pascals, let me just do a little math right here. To convert this to pascals, all you have to do is multiply this here by 1 kilopascal down here as a denominator and 1,000 pascals above as a numerator. And that will be equal to 101.325 pascals, all right? So that's basically the relationship between the kilopascal and the Pascal unit, all right? And then we have some other units, which to be perfectly honest, I don't anticipate us using that much. I'll just mention them. You have, sorry, go back to this. You have the millibar unit. You have the inches of mercury unit, which is more often used in reporting weather conditions in the United States. And then we have the pounds per square inch unit, which is basically an imperial unit. It's a combination of the non-metric unit, pounds over inches squared, all right? So those are the different units and the corresponding relationships between the different units when it comes to pressure. So 1 atmosphere is equal to all of this right here. Okay, so let's talk about, so this is just giving you some general information concerning the composition of air, which I mentioned before. As I said before, nitrogen is approximately 80%, or the atmosphere, the air that we breathe is approximately 80% nitrogen. Oxygen is just above 20%. And then of course we have much smaller amounts of the other gases, such as argon, carbon dioxide, neon, and so on, right? And as mentioned here, gases like xenon, hydrogen, and N2O are existing in trace amounts. Okay, so we talked about the dependence of pressure on the number of molecules and temperature earlier. We're going to say something more about this. This is just reminding us of what we said earlier with respect to the pressure, how the pressure is produced as a result of the continuous collisions of the gas particles with the walls of the container. And it says here, at a specific temperature and volume, the number of collisions depend on the number of gas molecules present, which makes sense, all right? The more gas molecules you have, the greater would be the number of collisions between the particles and the walls of the container, and therefore the pressure would increase. Now for an ideal gas, meaning a gas that basically follows the model of the kinetic molecular theory, the number of collisions is directly proportional to the number of gas molecules present. So if you look at this diagram here, it's showing you basically a demonstration of what we just said. Here we have 3 boxes containing different amounts of hydrogens, right? Here we have 1 mole of hydrogen under the conditions given here. Volume is equal to 22.4 liters and the temperature is 0 degrees Celsius. You see that the pressure exerted by 1 mole of hydrogen would be 1 atmosphere. If you were to double the amount of hydrogen under these same conditions, the pressure will be doubled. And if you were to reduce the pressure, or I should say reduce the moles from 1 to half, then the pressure will be halved as well. And this is true if it's only hydrogen present. But even if you have 2 different gases in the same container, for example, down here, we have this number of moles of hydrogen, Avogadro's number, which is 1 mole, and we have 1 mole of oxygen here. At the same temperature and volume, their pressures will be 1 atmosphere each. If you were to mix these 2 gases together in the same container, then what you'll find in this case is that the total pressure would be equal to the pressure exerted by each gas. Now, in this case, we have half a mole of hydrogen and half a mole of oxygen. So therefore, the total moles of gases here would be 1 mole. And the pressure is still 1 atmosphere. So it doesn't matter if you have different gases or if you have the same gases in the same container. Basically, the pressure is dependent on the number of molecules of the different gases that is present in a container, even if the gases, or even if the molecules, I should say, are different. Okay, so that shows you the relationship between the pressure exerted by the gas and the number of molecules or the number of moles of the gas present in a container. Okay, so that's basically what is stated here. The pressure exerted by a gas is directly proportional to the number of molecules present. Okay, let's talk about the dependence of pressure on temperature. So as stated here, what happens when you look at the relationship between the temperature and pressure is that there's a direct relationship between those two if the volume of the gas is fixed. So if you have a fixed volume of the gas and you increase the temperature, then the pressure would increase, all right? And the reason why that happens is because when you increase the temperature, you're increasing the kinetic energy of the particles of the gas. The gas particles will move faster and will collide with the walls of the container more frequently, and therefore will exert a greater pressure on the walls of the container, all right? So that's basically how the kinetic molecular theory is used to explain the dependence of pressure on temperature, all right? As you increase the temperature, you're increasing the kinetic energy, you're increasing the kinetic energy of the gas particles. The gas particles will collide with the walls of the container with greater energy and more frequency, and therefore will exert a greater pressure on the walls of the container. So that is being demonstrated in this diagram right here. So here we have a cylinder of gas at 0 degrees Celsius. The volume is 1 liter, and this is the amount of gas present. And under those conditions, the pressure exerted by the gas would be 2.24 atmospheres. If you increase the temperature from 100 degrees, I'm sorry, from 0 degrees to 100 degrees Celsius, same volume, same number of moles of gas, you'll see that there's a corresponding increase in the pressure, right? And of course, we can explain that based on the kinetic molecular theory. So that's stated over here. Let me move this aside here. Increased pressure due to more frequent and more energetic collision of the gas molecules with the walls of the container when the temperature is higher. That is how we explain the difference in pressure exerted by a gas at low compared to high temperatures, right? So basically we can summarize that under low temperature conditions, the pressure will be lower, but if the temperature is increased to higher values, then the pressure will be correspondingly higher, all right? So that's basically the relationship between temperature and pressure of a gas. Okay, so what we're going to do now is look at a series of laws which govern the behavior of gases, right? And in each of these cases, we can understand these laws based on the kinetic molecular theory. So the first of these laws is Boyle's law, right? And Boyle's law says, let me move this down here, that at a constant temperature, the volume of a fixed mass of gas is inversely proportional to the pressure of that gas, all right? So basically what this law says is that if the temperature is fixed and if the amount of gas is fixed, then there's an inverse relationship between the pressure of the gas and the volume. So basically what that means is that as the volume decreases, for example, the pressure would increase. And if the volume increase, then the pressure of that gas will decrease, okay? Now, we can express this mathematically in the form of this relationship right here. V is proportional to 1 over P, all right? So this is one way of expressing it. Another way of expressing it is this expression right here. P1 V1 is equal to P2 V2. In fact, let me just show you something here to show you how we get to that relationship. So as we said before, we can express Boyle's law in this way, right? And another way of stating this would be V is equal to K, a constant. Sorry about that, let me try this again. V is equal to K, which is a constant, times 1 over P, right? And therefore we can rearrange this to get P times V is equal to a constant. So what this is telling us is that under the conditions I mentioned before, and the conditions is that the temperature is constant and the number of moles or the amount of gas is constant as well. Under these conditions, the product of the pressure times the volume is equal to a constant. So therefore, another way of writing that is that P1 V1, which represents the initial pressure and volume, is equal to P2 V2, which would be the final pressure and volume. All right? So this equation here is useful because in this case here, for this equation here, if we can identify 3 of these terms, then we can rearrange this equation to solve for the 4th term, all right? And I think the next slide, oh, actually not this slide, but the slide after this, I think, has an example that we can look at using this equation. But before we get to that, let me move this up here. Let me talk about this graph here. This basically is a graph showing you the relationship between pressure and volume for a gas. And again, it shows you the inverse relationship between those two variables, as you can see here, as, how should I explain this? Okay, so the volume is here. Let's say the volume is at 8 mils, right? And the pressure of the gas would be somewhere below 1, maybe about 0.7 or so. And you'll notice that as you reduce the volume, what happens to the pressure? The pressure increases, all right? So that shows you the inverse relationship between the pressure of a gas and the volume of the gas, all right? And this diagram here shows you, again, in a more pictorial sense, the relationship between the two. So let me explain what's happening in this diagram here. So here we have a gas trapped in this vessel. You have a movable piston right here, where the pressure exerted is 1 atmosphere. So the pressure exerted by the gas here is 1 atmosphere. The volume of this container, or the volume of the gas, would be 1,000 mils, right? So if you multiply the pressure by the volume, you're going to get 1 atmosphere times 1,000, right? Which will be equal to 1,000. Now, if all of a sudden, let's say you reduce the volume from 1,000 mils to 500 mils, in other words, you reduce the volume by half. What happens to the pressure is, I wish I could get this thing. You know what? Let me do this. Let me get rid of that. Okay. So if you reduce the volume from 1,000 to 500 mils, then the pressure increases from 1 atmosphere to 2 atmospheres, right? So if you take the PV expression and multiply the 2 by the 500, you're going to get 1,000, which is equal to the 1,000 here. And then over here, if you reduce the volume further to 250 mils, in other words, you reduce it again by half from here, then the pressure will be doubled from 2 atmospheres to 4 atmospheres. And again, if you take the product of the pressure times the volume, 4 times 250, you see that that would be equal to the 1,000 that you'd have gotten here and gone here. So basically, you can see that in each of these cases, the product of the pressure times the volume is constant. And that is because as soon as you reduce the volume by a certain amount, the pressure would be increased to the same extent to maintain the PVs equal to constant. So that basically shows you how Boyle's law works. Okay, any questions so far? Any questions about Boyle's law and the relationship between pressure and volume? Any questions? Let me go back to this here. No questions, okay. Let me get rid of this again. Okay, so let's talk about this example, which I mentioned earlier, all right? So the question says in this example, an 8.00 liter sample of nitrogen is at a pressure of 500 torr. So the question is, what must be the pressure to change a volume to 3.00 liters? And it says here that the temperature is constant, right? So if you look at this question, you see that it's a Boyle's law question. Let me get my pen working here. Okay, so when it comes to questions of this type, it's very important, let me choose a different color. It's very important that you identify the different terms in this equation. So for example, the first thing I notice here is that they gave you an initial volume, which is 8.00 liters. So I would say that V1, the initial volume, is 8.00 liters, all right? And then I notice here that the pressure is 500 torr. So the initial pressure, P1 is equal to 500 torr. And I think I hate when this happens. Let me do this here, down here. P1 is equal to 500 torr. And I think there's a typo in this. There should be a decimal point here to make that 3 sig figs. And then it says, what must be the pressure? So the question is asking for the new pressure. So I'm going to put P2 equal question mark. That's what the question is asking for. And then it says to change the volume to 3.00 liters. So that means that the final volume, V2, is equal to 3.00 liters, all right? So the relationship, of course, according to Boyle's law, between the initial values and the final values is that P1, V1 is equal to P2, V2. Now, the question is asking for P2. And if you have done algebra in the past, you know that to get rid of this V2 here, we would have to divide both sides by V2 here and here, right? So the V2s will cancel out here. So you'll be left with P2 is equal to P1. Shoot, I hate when this happens. P2 is equal to P1 V1 over V2. And then we plug the numbers in. So the P1 is equal to 500 torr times V1, which is equal to 8.00 liters divided by V2, which is 3.00 liters. And all we have to do from here is our calculation. So 500 times 8 equals that, divided by 3. And somebody could check to make sure I'm doing the right thing, but based on what I see here, the answer is going to be equal to, when rounded off to 3 sig figs, 1330 torr. All right. So that's basically how you would do a problem of this type, a Boyle's law problem. All right. Any questions about this example? Any questions? Any questions? Okay, so one thing I want to say before I move from this example right here, whenever you're using Boyle's law to solve a problem like this, it's very important that you recognize, let me go back to my pointer here, very important that you recognize that it doesn't matter what units you're going to use for P1 and P2 or for V1 and V2, all right? What is important is that the units for the different terms expressing the same type of quantity must be the same. In other words, whatever the units that you use for V1, you have to use the same units for V2, all right? And the same is true for P1 and P2. Whatever units you use for P1, you have to use the same units for P2 when you're using the Boyle's law equation. So that's important because you could, for example, be given a question where, let's say, V1 is given in liters and V2 is given in, let's say, milliliters. In that case, you'd have to either convert the milliliter value to liters or vice versa before you plug the numbers into the equation to solve whatever the problem is, all right? So it's very important that you understand that it doesn't matter what the units are as long as they're the same on both sides for the volumes and for the pressures, all right? Okay, so if there are no questions about this particular example, let's move on now to the next law. What time is it, by the way? It's now 4:43. Okay, we should be able to at least do 2 more laws. So Charles' law is the next law that we're going to look at. And basically what Charles' law says is that the volume, let me skip this here. This is Charles' law. At a constant pressure, the volume of a fixed amount of gas is directly proportional to its absolute temperature. In other words, its temperature in Kelvin. And that's very important, right? The temperature that we're talking about must be expressed in Kelvin in order for this law to work, all right? So one way of expressing this law is shown by this equation here mathematically. V is proportional to the temperature, all right? Which means that you can also express it this way. V1 over T1 is equal to V2 over T2. And that is so because, go back to my pen function. Another way of expressing this equation mathematically, okay, where's my, okay. Another way of expressing this mathematically is V is equal to K times T, which implies that V over T is equal to K. So what this is telling you is that the volume divided by the temperature is constant. And therefore, because that is true, then we can therefore say, oops. So therefore we can say that V1 over T1 is equal to V2 over T2, right? Where V1 and T1 would be the initial volume and temperature, and V2 and T2 would be the final volume and temperature. And again, this equation is very useful because we can use this to determine one of these if we know the other 4, or I should say the other 3 values, all right? Okay, so that's Charles' law in a nutshell. So just to demonstrate what's happening in Charles' law using these pictures right here, again, we have a gas trapped in a cylinder. We have a piston right here, which can be used to keep the gas at a certain volume, but that's not the case here because basically we're making sure that the pressure remains the same, and all we're doing is increasing the temperature of the gas by heating it. And what will happen is that the volume of the gas will increase as a result of an increase in temperature, all right? And that is what is shown here. And that's because, of course, when you're imparting energy to the particles will move faster and therefore would force the piston upwards if the pressure is maintained at the same value as before, all right? So that's basically demonstrating pictorially the relationship between the volume and the temperature of a gas. Okay, before we get to this example, however, I want to go back to a slide that I skipped over, and that is this slide right here. Now, what this is showing you is the graphical relationship between the volume of a gas, in this case, the gas is methane, but this could be any other gas, right? But we're doing for methane, we're plotting the volume of a gas versus the temperature, all right? So basically what is happening is that in order to get the first few data points of this graph, the temperature is lowered for the gas and the volume decreases, which comes as no surprise. When the volume decreases, when the temperature decreases, the volume would contract, all right? Now we know that for pretty much every gas, if you cool the gas to a sufficiently low temperature, the gas will become a liquid, and therefore it wouldn't make any sense we try to plot the volume below that temperature because the volume will not change much. But what was decided by the powers that be is that based on the initial data points that was obtained before the conversion of the gas to the liquid, you're going to have an extrapolation of this line until it cuts the x-axis. And what this seems to suggest is that if the gas could have existed below the temperature, which represents its boiling point, basically, then what will happen is that the gas will contract to a volume of 0 at the temperature here, which is equal to minus 273 degrees Celsius. So based on that observation, what was decided was that this temperature here of minus 273, let me get my my pen here, this value of 273 degrees Celsius is defined as being equal to 0 Kelvin. And it represents basically the temperature at which, at least theoretically, where the volume of a gas would be equal to 0 at that temperature. And what that means basically is that if the volume of the gas is contracted to 0, no volume whatsoever, what that means is that the particles themselves of the gas will have absolutely no energy, all right? So therefore we're talking about no translational energy where the gas particles are moving in straight lines. There's no vibrational energy between atoms of the bonds, around bonds within this particular molecule. And there's no, what's the other form of energy? You have translational, vibrational, and rotational energy. Those are the 3 forms of energy, which at this point, the particle will have actually none of. And therefore, this brings us now to the relationship between the Kelvin scale and the Celsius scale. And that is given by this equation right here. The temperature expressed in Kelvin, the temperature in Kelvin is equal to the temperature in Celsius plus 273, all right? So that's the relationship between the Kelvin value and the Celsius value, all right? So that's how we ended up with the Kelvin scale. And the Kelvin scale, or the Kelvin temperature, is what you need to use in the case of Charles' law, right? So that's very important. Okay, so let me get to the next example. And in this example, they said, let me use a different ink here, that a 255 ml sample of nitrogen at 75 degrees Celsius is confined at a pressure of 3.0 atmospheres. It says if the pressure remains constant, what will be the volume of the nitrogen if its temperature is raised to 250 degrees Celsius? So again, this is one of those questions where you have to read the question carefully to identify the different terms. And the first thing that jumps out at me is the fact that the initial volume of the sample is 255 mils. So I'm going to write down here, V1 is equal to 255 mils. All right? And the question continues to say that the initial temperature is 75 degrees Celsius. T1 is equal to 75 degrees Celsius, all right? And then the question continues to say that the pressure is 3.0 atmospheres. So P1 the initial pressure is 3.0 atmospheres, all right? So what else are we given? It says if the pressure remains constant, right? So what that means that the pressure doesn't change, right? So let me just write here is constant. I'm sorry, folks, I'm having difficulty with this pen I'm using. That's why I'm getting all this stupid stuff happening. Okay, so basically the pressure is constant. And what that tells you, therefore, is that that will have no influence on the answer. It says if the pressure is constant, what will be the volume? So the question is asking for the final volume. So I'm just going to put V2 equal question mark. What will be the volume if the temperature is raised to 250 degrees Celsius? So T2 is equal to 250 degrees Celsius, all right? So in this case, we'll be using, okay, let me do it this way. In this case, we'll be using V1 over T1 is equal to V2 over T2, all right? What the question is asking for is V2. So based on what you should have learned in algebra, if you want to have V2 by itself, you have to get rid of the T2 by multiplying both sides by T2 here and here, all right? So that this T2 here will cancel out with this T2 here. So you're going to end up with V2 is equal to V1 over T1 times T2. And then all we have to do is plug in the numbers. However, remember the law says that the temperature values must be expressed in Kelvin. So that means that we have to add 273 to each of these temperature values here to get the corresponding answer in Kelvin. So for the 75 degrees, when we add, we do this here, 273 plus 75, the answer I get is 348 Kelvin. So I'm going to write 348 Kelvin. And then for T2, 250 plus 273. According to my calculation, this works out to be equal to 523 Kelvin. Oops. 523 Kelvin. So now we can plug the numbers in this equation right here. So V1 is 255 mils times T2, which is 523 Kelvin, all divided by T1, which is 348 Kelvin. And the Kelvin units will cancel out. So your final answer would be in milliliters. Your final answer would be in milliliters. So let's do the math. 255 times 523 divided by 348. So according to my calculation, this works out to be equal to 383 mils. So the final answer here would be 383 mils. So that's basically how that will be done. All right. Okay, are there any questions concerning this example? Any questions? Any questions? Okay, let's see here. What shall we talk about next? Okay, so the third law we're going to talk about here. Let me get rid of this here first. Okay, so the third law we're going to talk about here is what is known as Gay-Lussac's law. And, okay, why is this thing not moving? Okay, so Gay-Lussac's law says that the pressure of a fixed mass of gas at a constant volume is directly proportional to its Kelvin temperature. All right, so again, Kelvin temperature is very important when it comes to expressing Gay-Lussac's law. So basically, we can write this as the pressure of a gas is equal to a constant K times the temperature in Kelvin. Excuse me 1 minute. Okay. Or we can express it this way. P1 over T1 is equal to P2 over T2. All right. And again, if we can identify 3 of these terms, we can find the 4th one by rearranging this equation to solve for that term, all right? So this is very similar to what we saw in the case of Charles' law. The only difference is that instead of V1 and V2 up here, we have P1 and P2, all right? Okay, so let's go directly into this example right here. Excuse me. So let me go to my pen function. So the initial, in this question here, they gave you the initial temperature, which is 40 degrees Celsius. Excuse me, the initial pressure is 2.15 atmospheres. Excuse me, I'm sorry about that. And the final temperature is 100 degrees, and the question is asking for the final pressure, all right? So let's write down what each of these terms represent. So T1 would be 40 degrees, damn it. T1 is equal to 40 degrees Celsius. We have to convert that to Kelvin. So 40 plus 273 equals 313 Kelvin. And then P1 would be equal to 2.15 atmospheres. And then T2 would be equal to 100 degrees Celsius, which we have to add 273 to, and that will give us 373 Kelvin. And what the question is asking for is P2. All right. So we're going to use P1 over T1 is equal to P2 over T2. And again, to get P2 by itself, we have to multiply both sides by T2. So this will cancel out with this. So we're going to end up with P2 is equal to P1. P2 is going to be equal to P1 over T1 times T2. And then it's all a matter of plugging the numbers in. So P1 is 2.15 atmospheres times T2, which is equal to 373 Kelvin. I'm tired of this. Divided by 273 Kelvin. And let me do that calculation here. 2.15 times 373 equals divided by 273. Oh, wait a minute. I made a mistake. This here, I don't know where I got this from. This here should be 313, 313. All right, so let me do this over. So it's 2.15 times 373 divided by 313. And according to my calculation, this works out to be equal to 2.56. 2.56 atmospheres. And that's basically how that is done. Okay, any questions about this particular example? Any questions? Any questions? Let me check the chat here. Okay, no questions apparently. So far, so good. Okay, so let's see what's next. Okay, so far we have learned 3 laws, right? In fact, let me get out of this here. And I think this will be the last thing we're going to talk about before we end today's class. So let me open up my writing pad here so I can explain this a bit better. Okay, so far we have learned 3 laws. And let me just summarize them here. We learned that PV is equal to a constant, right? This is Boyle's law. So I'm right, Boyle's here. All right. And this is only true if the number of moles and the temperature is constant. So in order for that law to work, these 2 factors must be constant. The next law we learned was Charles' law. And Charles' law says that V over T is equal to a constant. Now, in order for that to be true, the number of moles and the pressure must be constant. All right. And then the third law we learned was Gay-Lussac's. Gay-Lussac's. And what this law says is, I hope I'm spelling his name right, is that P over T is equal to a constant, right? This is true if the volume and the pressure, volume and the, yes, volume, hold on, wait a minute, and number of moles, I'm sorry. The volume and the number of moles are constant. I don't know why I blanked out a while ago. All right, so basically for each of these laws to work, there are two terms that needs to be held constant, right? So this begs the question, what if everything changes? What if the pressure, the volume, and the temperature changes and the number of moles? Well, let's deal with the number of moles later on, right? What if the temperature, the pressure, and the volume changes simultaneously? Then basically we can combine these three laws into one law, which is known as the combined gas law. And the combined gas law, write that down here, the combined gas law is PV over T is equal to a constant. So basically, what this is saying is that if you multiply the pressure by the volume and divide by the temperature, then that will be constant if the number of moles is constant, right? So if we're talking about a fixed amount of gas, then this would be the combined gas law, which govern their behavior, the relationship between pressure, volume, and temperature. So another way of expressing this is what I have here in the PowerPoint. P1 V1 over T1 is equal to P2 T2 over V2, all right? So it's a combination of Boyle's, Charles, and Gay-Lussac's law, which I don't have here, but basically it's a combination of those three laws that leads to the combined gas law. And as I said before, we use this law when these three terms change. So if you're starting with a gas where the pressure is P1, the volume is V1, and the temperature is T1, and then you change all of these three to P2, V2, and T2 respectively, then this is the relationship between those six terms. And therefore, you can use this equation to solve for one of these if you know the other five values, all right? Okay, one last thing I'm going to talk about, and then I'm going to call it a day. And that is the whole concept of standard temperature and pressure. Now, this is important because very often it is necessary for us to make meaningful comparisons between different gases, right? And the best way to do that in some situations is that we have to ensure that the temperature and the pressure of the gases are the same, right? So if we ensure that to be the case, then we can make some comparisons between gases under those conditions. For example, we can see which gas is more dense, which gas would have a greater molar mass, and all of that, all right? So the powers that be, I think it's IUPAC, the International Union of Pure and Applied Chemists, they have decided that these standard conditions would be, as you see here, the standard temperature would be 273 Kelvin, which is the same thing as 0 degrees Celsius. And the standard pressure would be 1 atmosphere, which is the same thing as 760 millimeters mercury. So basically, those are what we call the standard conditions of temperature and pressure, otherwise known as STP. So if you see in a question, this expression here, STP, then you should immediately understand that it's talking about the standard conditions of temperature and pressure, where the temperature is equal to 273 Kelvin, and the standard pressure is equal to 760 millimeters mercury, which is the same thing as 1 atmosphere. All right, so those are the standard conditions that has been defined. Okay, so let's look at this example right here. It says a sample of hydrogen occupies 465 mils at STP. If the pressure is increased to 950 torr and the temperature is decreased to minus 15 degrees Celsius, what would be the new volume? All right, so this one is a bit complicated than the others that we have looked at so far. And that's because in this case, we are using the combined gas equation. So let me just write down the equation up here. And that is P1 V1 divided by T1 is equal to P2V2 divided by T2, all right? So basically we have to read this question and identify the different terms. Now, the first thing I would identify is the 465 mils here. That would be V1. So let me just write that down here. V1 is equal to 465 mils, all right? Oh my God. V1 is equal to 465 mils, all right? Now, the question also said that the conditions would be STP conditions. And that means that the temperature for T1 initially would be 273 Kelvin, and the pressure would be equal to 760 torr, all right? Then we get to P2. P2 is equal to 950 torr, and T2 will be equal to minus 15 degrees Celsius. But we have to add 273 to that to convert it to Kelvin. So 273 minus 15, according to my calculation, this works out to be equal to 258 Kelvin, all right? So what the question is asking for is V2, the new volume, all right? So we're going to use this equation, but we need to solve for V2, all right? Which means that we have to get rid of the P2 and the T2, which means that we have to multiply both sides by T2. So we multiply by T2 here, and we have to divide both sides by P2, all right? So therefore, what we'll end up with is T2 is equal to P1 V1 times T2 divided by P2 T1. And all we have to do from here is plug the numbers in. So P1 is equal to, this should be P1 right here, by the way. I'm sorry about that. 760 torr times V1, which is 465 mils, times T2, which is 258 Kelvin, all divided by P2, which is 950 torr, times T1, which is 273 Kelvin. And basically it's straight number crunching from here. 760 times 465 times 258 divided by 950 divided by 273. And according to my calculations, when rounded off to how many sig figs? We have to round this off to 2 sig figs. So the answer becomes 350. And the units would be in Kelvin. No, I'm sorry. The units would be in liters, or I should say milliliters, because the torr units will cancel out here and here, and the Kelvin units will cancel out here and here. So your final answer would be left in milliliters. So this is the final answer right here. All right. Okay, are there any questions about this example? Any questions? Any questions?
Yes, can you hear me?
Yes, I can hear you.
It's personal to me though. Should I still
okay.
ask you?
Well, if you don't mind other people hearing it.
Okay, so my high school courses are during the only times that are left available for me to schedule this week.
Your high school what?
So I'm still taking high school courses that are in the morning, and the only time that is still available for me to test at the Ocala campus is taken.
Hold on.
Besides the times that I have classes.
So you're saying that the only times available for doing the test at the Ocala campus is conflicting with your high school schedule?
Yes.
And that's straight up to Friday?
Yes.
Okay. Hold on 1 minute. Let me get out of this here. Okay. mm, okay, that would be the only thing I can probably suggest is that you'd have to do it sometime, since if that's the case, the only thing that is left for you to do is to do it sometime next week. The earlier, the better. But that means now I have to contact the testing center and let them know about that. Okay, tell you what, let me make sure I have your name down. You are you Alexandra Paddyfoot?
Yes.
Okay, let me see here, Alexandra. Okay, so if you can't do it on the 1st, what day next week you will be able to do it? According to my calendar here, next week runs from the 4th to the 8th of October.
I could do it Tuesday after 3:15.
Okay, Tuesday the 5th. Okay, so let me make a note here. All right, now what I would do, okay, so what I'm going to do is call a testing center. I don't think I'll be able to call them now because I think it's too late, maybe, I don't know. Plus I have a class immediately after. But I'm going to call them tomorrow. So what I'm going to do is call them tomorrow and let them know about your situation. And then I'll email you, and then you can go ahead and make the appointment for next week, Tuesday.
Okay, and I just realized I could also do it during this class period on Monday. If that's better.
I wouldn't want you to do that because I don't want you to miss the material that we'll be covering in today's class, even though it seems as if some of your fellow students have missed today's class because there are only 9 students here and there's a total of 21 students registered in this class. But I wouldn't want to suggest that you missed, the class for the sole purpose of doing the test. So I would just say, let's stick to the 5th of October.
Okay, sounds good. Thank you.
All right. Okay, now I see 2 questions in the chat. Okay, or 2 statements. You can take it both. Oh, so Caleb is saying that you can take it at 10 p.m. Oh, 10 a.m. and 4 p.m. Okay, I mean, those are the times, I guess, that are allowed. In my conversation with the lady at the testing center, it seems as if they're very restrictive about the times, which is kind of different from before. I don't know why, but I think it has to do with the fact that they are doing more external exams for other people, and therefore that kind of limits the amount of space and time that they have for the students here. I don't know, but things are changing over there in ways that I don't understand, unfortunately. Okay, are there any, okay, somebody's asking, are the formulas provided? Yes, the same tables that have been posted in Canvas, which gives you the conversion factors, the periodic table, and all that good stuff will be made available to you guys during the test. So you do not have to bring your own copies, all right? So that's an answer to the question being posed by Rosianna Bizra, all right? Okay, any other question? Well, can't be any more question because it's now 5:15. So I hope you guys do well in the test, and I'll see you guys next class, which is on Wednesday. So take care and have a good evening.